Good afternoon, everyone, or good morning, depending on which time zone you're in. Thanks for showing up, and welcome to today's online seminar for zoning and its effects on condensing boilers. This is about that, but it's also about how it affects any kind of boiler. So we're going to do a lot of stuff here. My partner today, again, is Scott Boutelier of our Langley office. Morning, Scott.
Good morning, good afternoon, everybody. This is the morning time zone that Mark's talking about here on the West Coast. So
we have to get
I'm got my caffeine. Yeah, Mark, thank you for adjusting my headphones remotely. I got a haircut in the weekend and they were falling off here, so we're all ready to go here. My headphones are stuck to my head, and I'll be ready to roll here. I think I'm going to be looking after the questions today, Mark,
and the
Q&A stuff in the chat. Try to get Mark so he can keep on focusing on the presentation while you guys can shout out your questions. You have the tabs on the bottom here, and the Q&A is where we prefer you kind of ask those questions. That way there we can broadcast those to the group. If you do prefer to have those questions answered privately, then you can mention that and we will do that. If there are questions that, Mark, it would be better to kind of answer, based on the presentation, or, I just don't know and just don't want to lie to you today, I will hold those off till the end, and Mark can look after those, and we'll try to kind of gang up on those questions at the end and get those in. And as usual, like I say, if there's something that you have to go for some reason, but you do have a question, and we don't get to you by the end of that, by the end of this presentation today, Mark and I will reach out to you via email or some other format to get those answers to you. So please, if you have a question, this is the great time to answer those or get those questions out there so they can get those answers to those queries that you have. Other than that, I don't ramble on much more. Just Mark, I'm really going to look forward to this particular presentation. I had a little quick peek at it. You sent it yesterday, and it looks like a good one. So I'll be sitting here taking it all in.
Thanks, Scott. This presentation is partly going to go into some of the things that Scott's going to talk about later about application piping. So some of these things I'm not going to go into a lot of detail because he's going to cover that in a separate presentation. But I think it's important that we understand some of the logistics of the piping so we can get going at figuring out how this is going to affect us. We look at boilers and how we put boilers in buildings, and historically, we had a building with a boiler in it, and we hooked up the piping, and we had maybe one pump, and we pumped water through the radiators. The boiler's control was set at the hottest temperature we needed for the year. So we had an aquastat on the boiler, and if we had baseboard radiators, the aquastat was set at 180 Fahrenheit. If we had cast iron, it was set at 160. And that's what we had. And we didn't really have a lot of control over what happened in the space. People in the house had to just live with what it was when it was warm outside, and the boiler was making 180 degree water. They were trying to shut manual valves on rads, and a lot of times they didn't work. And you guys know that if you try to close a valve that hasn't been closed in 10 years or 2 years, it doesn't work very well. So this is all the way we started. And even when you go back far enough, we didn't even put a pump in it. Gravity fed systems were really big pipes to reduce the friction loss, and we let the hot water go to the top and the cold water fall down to the bottom, and that's how we heated the building. So things have changed over the years. The first thing we did was we added a thermostat. So the thermostat was the device that allowed us to control when the boiler turned on and off from the space. But it didn't control anything but really the room where it was in. So the thermostat was located somewhere in the central part of the home where it was comfortable to most people hung out at. And when the thermostat was satisfied, it turned the boiler off, and the house cooled down. It turned the pump off and the boiler off, and so everything starts to cool down. The piping, the boiler all started to cool down. And when the room lost enough temperature, we turned the thermostat closed again, and we turned the boiler back on. So we had these wide swings in the room temperature because of that. We had the still boiler set at the maximum temperature we needed. So on a warm winter day, we threw a crap load of heat into it, and then we let it cool off. So the only room in the house, a lot of times it was comfortable, was the room where the thermostat was in. Now, fortunately, during these periods, and I grew up in some of those periods, that everybody congregated in the living room anyways. We were all sat around the same TV and we watched all the same shows, and there wasn't a whole lot to do. We added outdoor reset to try and make things more comfortable. And the second benefit of that is it also made it more efficient. So the outdoor reset then looked at the outdoor temperature and adjusted the water temperature to base that. And so it was a little bit better for gaining heat loss and heat gain, but the thermostat, again, was still in the living room. And that meant that people in the kitchen were hot and people in the upstairs or in the bathrooms, they were cold. The thermostat still cycled the boiler, but it was a little easier to deal with. When we started looking a little deeper at modulating burners, so we started replacing the Vitola with an on-off burner with a CU3A or a Viessmann or some other kind of burner with a modulating burner. Now it was, again, a little bit better because now we could adapt the heat input to the heat loss a little bit better. But as things went along, we all saw what happened with the market. Houses got bigger, they had more rooms, people's lifestyle changed. Instead of everybody living around in the living room watching Howdy Doody and any of those other shows, All in the Family, whatever the show they were watching when they were congregated as a family, as a group, the internet started. So people had TVs in multiple rooms. We had telephones, we had internet, we had game systems, we had all sorts of things that allowed us to split up the different parts of the building. And because the buildings were bigger and closed up a lot more, we found that, that thermostat in the living room just wasn't cutting it anymore. So what did we do? We started to add zones. We started to add valves or pumps. And the idea was to zone buildings into individual compartmentalized spaces so that we could control the heat within the space. And this is where we started to see some challenges with how we manage the boiler plant from the thermostat. So our boiler rooms went from this to this. And we had zone valves, or we had pumps, we had multiples of them, we had multiple thermostats. And the mindset was still, I want to turn my boiler off whenever the thermostat's open. But now we have a bunch of thermostats. So we have to look at how we do that, or why we even do that. Look at this system here as an example. This is a low mass boiler, so a Viessmann wall hung boiler, which has very little water on it. We talk about mass, we talk about high mass and low mass. It's really about the amount of water that's in the bucket. So the bucket in the Viessmann is about a gallon for 125,000 BTUs, and for a high mass boiler, 13 gallons. So the difference in between low mass and high mass. The low mass boilers also have a higher pressure drop. So that means that the water going through them loses more pressure as it goes through the heat exchanger. Now, that now means that we have to maintain flow through this boiler at a certain rate. If we don't maintain flow through the boiler at a certain rate, we will either not be able to run the boiler, or we'll get too hot, the delta T goes too high. And when we first started doing this, we started doing this just replacing the cast iron boiler and throwing the low mass boiler on the wall, and we really didn't do anything to the system piping or the connection between the system piping. And when we had zone valves closing, we had issues with flow through the boiler. Now, we could have done to a variable speed pumps, but at that time, variable speed pumps were expensive. So what we did is we went through a fixed speed pump and put a pressure bypass. That solved the flow issue through the boiler because we were always circulating the same water through the heat exchanger. But because of the low mass boiler, it also caused short cycling because there wasn't a whole lot of water to heat here. So the boiler would short cycle. And again, when the thermostat's open and closed, the boiler would go off. So we added primary, secondary. In this case here, a little less header, but we see we could also done it with closely spaced T's. And that solved the flow issue here. We had to maintain a constant flow through the boiler. It gave us a little bit of a break between the system. We still did the fixed pump with the pressure bypass, or in more recent ones, variable speed pumps. But we had a more consistent temperature from primary to secondary, and it was a little easier to control the low mass boiler. But we could have also added mass. So we might have said that in the situation here, the boiler's still short cycling because I just don't have enough water. When one zone is calling, the boiler's going to short cycle. So we add mass. So we added the buffer tank, which could have been 10, 20 gallons, whatever size we figured we needed for the system. And the buffer tank then became a mass of water that the boiler would heat, and then the heat would be drawn from the building. So if only one zone was calling, it could pull most of its energy from the buffer tank. And when the boiler saw the buffer tank cooling off, it would run a longer cycle to heat up the tank. We can do the same thing with a high mass boiler. So the high mass boiler being 13 or 18 gallons itself in the Vita Crosso boiler, it is its own mass. So now we can get by without the primary secondary again. And we still have some flow conditions where when the valves open and close, the flow changes, but the high mass boiler has very low pressure drop. So it doesn't really care, and it doesn't need flow to run. So we've solved the flow issue. But we also have to deal with other things like the controls and the start-stop functions. We also see systems that had pumps instead of valves. So now instead of 5-zone valves or 4-zone valves, we have 4 pumps. And downstream of those pumps could have also been valves. We'll get into that in a little bit. But the idea here is that whether it's zone valves or whether it's pumps, the same logic goes into play. We still have to deal with what happens when all of these pumps or all these valves are turning on and off by thermostats. What do we do with the boiler? And we also have systems that have a combination of things. And maybe they're all the same temperature, maybe they're different temperatures. And we'll talk about that as we go through here. So we have zone 1 here, which is all pumps, probably on a multi-zone control. Zone 2 here, which is 1 pump and multiple zone valves, again, probably on a multi-zone control. We have something like a snow melt system, which will have its own independent control, and it's going to operate based on that energy that we need when we need to melt the snow or heat the pool or whatever that's against. Again, if we do this in a high mass boiler, we can eliminate primary secondary because higher mass, and if the flows are changing here, that flow is going through the boiler, but because of the mass of the boiler, it doesn't make that much difference. But we see here we have these thermostatic mixing valves. And we need those in some cases because if I'm going to heat my domestic hot water tank to 140 degrees, the boiler has to go to 160 to provide energy to it. So that means I have these 13 gallons of water sitting at 160. And if my system here are only looking for 110 or 120, we have going to have 110 or 120 degree water we want here, but we're going to get 160 degree water when it switches back out of DHW. So these valves kind of limit that. The Vitadens, when we see low mass, we also showed it in the drawing, but it's not as big a deal here because again, there's only a gallon or maybe 4 gallons on a big one of water in here, so it's not a big deal. But when we have 13 or 18 gallons of water, it may be an issue. So we had the thermostatic valves just as a safety to protect this loop from its higher water temperature. But we saw we were to move that water to there, we have a pump. So let's look at what we do when we have a pump. We have a pump curve. So when you're looking at supplying or selecting a pump, you're going to see a chart that looks like this with flow across the bottom and head or feet of water across the side. And your pump will be able to move a certain amount of water against a certain amount of head. And we'll see a line that looks like this on our chart, which is the pump curve. So the pump curve then tells me that at this flow rate, we can move whatever head where they intersect. But not all pump curves are the same. So picking the pump is also a matter of checking to make sure that the curve on the pump we're picking is going to be in the right direction or the right parameters. Because we may, with starting to close and open zones, we may have a pump curve like this that doesn't work. But it might be a more flat curve because as we change flow rates, it doesn't change the head a whole lot. So we need to select the pump based on our application for zoning and not zoning and these type of things. We also see 3-speed pumps, now quite common. And so we have multiple speeds. So we select the speed of the pump based on whatever flow and head parameter we want. But the real reason why I pick a different speed on a pump hasn't really a lot to do with the flow as much as it has to do with the temperature. Variable speed pumps, they'll have a nominal flow rate, and they'll be able to speed up or slow down, which you see really just pushes it into a different curve. And as we slow down, again, we have to look at its minimum speed, what head can it push, at its maximum speed, what head can it push, and we have to figure out that pump fits into that group of head and flow parameters. Now this chart here shows it's basically a single pump with a VFD, variable frequency drive. more of a commercial application. So, I mean, either it doesn't really matter whether it's that or it's a both ways modulation pump, delta P pump, whether it's a pump that uses a 0 to 10 control. The theory is the same. We're going to speed or slow down the pump based on what we need to move water. But at some point, every pump runs into the point where it can't pump water anymore against the head it's pushing against, what we call the deadhead point. And even with a variable speed pump, we look at variable speed pumps as, this is the cat's butt. You know, we're gonna be able to put that pump in there and it's going to change the speed. But at some point, we're not going to be able to pump water anymore, depending on what the head it's pushing against is. And I want you to remember head, because we're going to talk about that a lot as we go through here. Every pump has an optimal range, which we call the knee of the curve. And this is where you should be selecting the pump. You shouldn't be picking a pump that's way out here or way out here. You're picking something in the optimal range. And within that optimal range, the pump manufacturer will say, we can move water between here and here, but somewhere in that range is the best performance point, where the pump is the most efficient. And when we start looking at variable speed pumps, this is an important thing to look at, because we're not always going to want the best efficiency point in the pump we pick. Again, 3-speed pumps, why do we use them? Well, I select the speed not really based on the flow I want, although that's an important part. It's more about delta T. If I want to change the delta T across a heating loop or a boiler, I can change the flow rate. That changes the delta T. So if I'm going to run it at a lower flow rate, though, I also have to deal with the fact that my head pressure is going to change, head capacity is going to change. So you want to make sure that you stay within the pump curve if you're picking the lower speed. Now, when we look at variable speed pumps, like I said, you have the best efficiency point, but we don't always want to run the pump at the best efficiency point. In this example, whatever pump was picked here, we want to pump against a 70-foot head, but you can see that when the pump gets down to 80% of its speed, so we've gone from 100% to 80% with whatever control's doing that, we fall off the pump curve. It can't pump water against 70 feet of head at that speed anymore. So we only have a 20% modulation capacity on that pump before it quits pumping water. So we might pick a pump, either use a different efficiency point, or we'll pick a pump that has a higher efficiency point at the different flow rate, because at 75% efficiency on this pump, I can modulate it all the way down to 60%, which means I have a 40% modulation range, which is a pretty good range on a pump. So you don't always want the best efficiency point. You want to look at where that point works into your flow and head requirement throughout its entire modulation range. But what do we need pumps for in the first place? Well, we want to move BTUs. We want to move water from the boiler to the radiators, and when it's used up, we want to bring it back. And the amount of water we use, the amount of water we move is based on how much BTUs we want to move. So there's a formula which helps us do that. And the formula basically has heat transfer, fluid flow rate, a delta T across the system, and a constant. And a constant really is about the water or whatever liquid we have, the specific heat of the liquid, BTUs per pound per degree Fahrenheit. It takes 1 BTU to raise 1 pound of water, 1 degree Fahrenheit. So that's kind of how we get the factor for what we're doing here. And then the time factor, usually in minutes. So together they become a constant, which, we don't have to remember this anymore because we have the constant number. We just use the number. So there'll be a constant number for water. There'll be a constant number for glycol, and you can pull that information from the internet to know how to size your pump. So what we need to mix the formula around a little bit. So we say flow rate is energy in over delta T times the constant. So this is how I'm going to determine it. So let's look at a system where we have a radiant floor zone and we have a heat loss of 50,000 BTUs. So the boiler has to move 50,000 BTUs from the boiler to the radiators and back. And we decided we wanted a 20 degree Fahrenheit delta T. So when we use the formula, we can see that it's GPM over BTUs per hour over delta T times 500. And this is where we get the time factor and the specific gravity, right? So in this case here, water is 500. So if we go to 500 times the 20 delta T, we can see that gives us a denominator of 10,000. And we have the 50,000 BTUs on the top here. So 50,000 over 10,000 And that means to move 50,000 BTUs with a 20-degree altitude through this building, I need to move it at 5 GPM. This is how we figure the flow rate. But remember, that's only half of it, right? The other half is head. So we have to look at two things. First is the static head. Static head is basically the weight of water in a pipe. And it doesn't matter what the size of the pipe is. It just has how tall is the pipe. It's like air pressure. At sea level, we're 14.7 PSI, and atmosphere and space is like nothing or very little. Water's the same way. The weight of water sitting in the pipe. In 120 foot building, if we were doing this as a domestic water system, let's say like a booster pump, we would have to have 52 PSI more pressure at the bottom than we did at the top. So if I want 50 PSI in my taps, I'd have to have over 100 PSI at the basement to get the water to the top because of that head. Now, with a hydronic system, it's not quite that black and white because whatever goes up comes down. So we have to overcome that head at some point. But once we have the water moving, the static head isn't a whole lot to deal with. What we do need to know, though, is in relationship to the pump and the piping, because we have a thing called static lift. And static lift is the suction of the pump. And again, comparing that to a domestic system, we see, like a rural well with a jet pump. And people say, well, I need to, pump water or whatever. But when they look at the depth of the well, the static lift is going to determine whether that pump can prime itself. So static lift is the suction pressure, and then we have the static height on top of that. And together they determine what the pump can push. The other thing is friction loss. Friction loss on the piping. And we see charts like this. You can pull these charts from the manufacturers of the pipe, and you can say that, as I move water, more volume of water through the piping system, my head loss goes up. So if we're moving, in this case, 300 GPM across this piece of pipe, there's a 5 PSI pressure drop, and times 2.13 tells me that that friction loss in that pipe is 11.5 feet of head. But the chart gives it in the reverse. So let's look at a 1-inch pipe at 2 GPM, only has 0.38 feet of head for the 100 feet. But if I move 40 gallons a minute through that 1-inch pipe, my pressure drop goes to 95 feet of head. That's a huge difference for a pump to try and deal with. So we have to make sure that we calculate the friction loss, put the right size pump in. We talked at the beginning about the gravity systems, and they had great big monstrous sized pipes because they weren't pushing water. They were letting it naturally go up and come back down. And that meant we had to have that pump, that bigger pipe, so the friction loss was low. Same thing with our systems. And we see one of the common areas where we see this as a problem, those guys putting DHW tanks in because they say, well, the pressure drop in the boiler and the pressure drop in the tank, but they don't take the pressure drop into the piping between the boiler and the tank, and then they can't figure out why it won't make hot water. The boiler cycles on the temperature and they can't get heat into the tank. It's because the pressure drop in the pipe is too high for the pump you picked. Then we have the control valves. And a couple of things about control valves is that we need to know the flow and the pressure drop to size these, but we also need to know the size we need to move and the configuration. So there's 2-way valves, there's 3-way valves, there's 4-way valves. In a 2-way valve, it's really just open and close, right? It could be proportional, but it's still open and close. It's either moves water or it doesn't move water. And this is going to be something we're going to come back to as far as managing the pressure drop in the system. 3-way valves come in a mixing configuration. That's 2 in, 1 out, or diverting, which is 1 in, 2 outs. They have different interior configurations, and they have different purposes. So it's important that we know the application we're using it for. And 4-way mixing valves. Now, these can be in different configurations or different types of mechanisms inside. The most common one we see nowadays in the smaller sizes is a ball valve. They're inexpensive to make and they're easy to build. Once we get into larger valves, though, we see more gate valves. And gate valves are position important. There's an in and an out to a gate valve or it won't work against the back pressure. Butterfly valves really aren't used in control. They're used for isolation valves because they have really lousy proportional control. You can close a butterfly valve about 90 or 85% and it has almost no effect on the flow. And then that 0 to 100% happens in the last 10% of the travel. Same with gate valves. We don't see these used in proportional valves just because they don't make sense to do that. So let's look at a system where we have multiple temperatures. We have an 80 Celsius loop, we have a 70 Celsius loop, and a 45 Celsius loop. And the boiler can only make one temperature. So when all of them are having a call for heat, the boiler has to make water hotter than 80 degrees. So we put control valves here and here that control the water temperature downstream. So if this loop's asking for 80, but this loop's only asking for 70, we're mixing it together here to get that right temperature. So this is a mixing valve application. When we were using cast iron boilers, we used four-way valves for this. We took the water from the boiler and the water coming back from the return, and we mixed it together to lower the temperature going out here so that it met the heating curve that we wanted for that loop. But the boiler itself, we wanted to keep hot. So we took also the hot water from the boiler and mixed it with cold water from the system and elevated this water here to protect it from condensation or from thermal shock. You can see, though, that if I was going to put a condensing boiler in, what's going to happen to the boiler if I keep raising this temperature? I'm going to reduce its efficiency. So if you're replacing a cast iron boiler that has control valves, then you also need to replace the control valves. And they should be three-way valves so that the coldest water sees the boiler. So this is a difference between two different types of mixing valves, four-way and three-way. So condensing applications, we want to use three-way. You don't want to use four-way. But I said there was two different configurations, mixing and diverting. So let's look at what happens with the different types. You've got two inlets and one outlet on a mixing valve, and one inlet and two outlets on a diverting valve. They can both be used in an application that's very similar, but they're installed and configured differently. So I have a mixing valve, and you see where the pump is pumping water through the fan coil here, and either through the valve or back to the boiler and then coming out from back to the boiler here. So what happens in here is my flow rate through the coil is always consistent, which means my delta T is always consistent. I might reduce the surface temperature of the coil by reducing the water temperature, but the delta T is always the same and the velocity is always the same. So as the valve changes temperature, it doesn't change the velocity, so I don't get crap settling in the bottom of the coil, which may cause me a problem later. But a diverting valve, we're using on the same fan coil, we see the pumps in a different place. And you'll see a lot of commercial buildings built like this because the engineer wants to share this pump with multiple fan coils. And this reduces his design and installation costs. But what happens here is when I reduce this valve, I send some of the water back this way. What happens here is we actually reduce the flow rate across the coil, and that changes the delta T on the coil. So we don't have a consistent surface temperature, and we don't have a consistent delta T. And because the flow rate's low, we actually might settle debris in the bottom of this coil. And if this is an air makeup coil that's seeing cold outside air in the wintertime, this could lead to a coil freezing. So we have two different ways of the same thing, but you see the configuration is different. Now, inside the body of the valve, we're specifically looking at ball valves here. We have two different types of ports, full port and standard port. And full port just means the hole is the same size as the piping size we're dealing with as far as flow goes. But we also have what they call proportional guide or characterized guide or V ports or equal percentage. Every manufacturer has a different pet name for these. But if you look at the balls, they have different shape holes, kind of a teardrop shape. And that means as the ball opens, it proportionately opens. So a little bit open to a maximum open. The rate of flow is linear, which means we go from 0 flow to 100% flow in a very smooth transition. So this is what we talk about proportional valves, that they're going to have equal flow across the valve. Now they could be electric or thermostatic. And most of these are going to be proportional, but they could also be on and off. A three-way valve could be on and off. When they're on and off, this characterized guide isn't that important because they're just not really spending time in the middle. But all of these valves have one common design factor, a value called CV. And this is where the pressure drop in the system is important to deal with, because CV is defined as the flow rate through the valve at 1 psi pressure drop. So if I have a 1 psi pressure drop across my system, then this is the flow rate I'm going to get. In this case here, 3 CV gives me 3 gallons a minute at 1 pressure drop. If I had 10, it would be 10 GPM at 1 pound pressure drop. So we need to know this number in relationship to our system design and how we're going to control the different valves in the building so that we can make sure we pick the right valve. So here's a system with a pump, sized, fixed speed pump, sized to pass water through 3 different loads. and we have control valves on each load tied to a thermostat or some kind of a control. And when they're all open, we'll say this is a 15 GPM pump. We have 5 GPM in each port. We have on each load, we have a pressure drop that we've known because we've sized the valve, we sized the piping, we sized the radiator. We know what we're doing with pressure drop there. But as soon as I close a valve, as soon as this valve stops calling for heat, this pump's still pumping 15 GPM, and I no longer have this pressure drop or this load. What I'm going to do is I'm going to take that 15 GPM and try to push it through 2 loads, which means that I'm going to increase the volume of water. And what does that do to the pressure drop? It increases the pressure drop. So in some situations, I can actually closing this valve would stop heating these zones because I take it off the pump curve. The pressure drop would go up so much that I wouldn't be able to pump water through the zone. So again, we 15 GPM like this, and we close that valve, we have higher GPM here, which means we're not going to get, potentially, not going to get the flow that we want because the pressure drop goes up, the head friction loss goes up. One of the ways we can solve that is maybe with a 3-way valve. But when we look at a 3-way valve, we have to consider that whatever the pressure drop we calculated here has to be the same here. So we might, depending on the system size, commercial building, we probably have to add a balancing valve here. But now you can see that we can then bypass water and the pressure drop remains the same. The friction loss remains the same. The thing we have to deal with, though, again, with the diverting valve is remember that if it's a proportional valve, the delta T is going to change. So if this is not just open and closed, as soon as I change the water temperature, the delta T here. So this is, we have to consider that, this is not going to be too cold at this end. I've worked in some buildings that, there's a building in Kitchener that used to be a department store many years ago, and they turned it into offices. And when it was a department store, it was one big open space. So they didn't care. The radiator went from one end of the building to the other end of the building on the one floor. But when they started breaking up into offices, they ended up with a cold zone in the last, because the delta T was too high. They started making any changes. So what if we change a variable speed pump? So now we have a 15 GPM when they're all open. In this case here, we shut the valve here, and the pump knows that we've got a higher head loss, so it's going to reduce its speed. And now we have GPM here that's the same. This eliminates the issue with friction loss, but we start to see other issues. So here's an example. We have a zone like that where we have multiple radiators downstream of a mixing valve. Now we have 120 degrees coming from the boiler because the zones are asking for 120. So the valve's really just open all the way. The water's going through the rad, it's coming back, and most of the water, all the water is going back to the building. So we have this 20-degree delta T we asked for. But now we say, well, we only need 100 degrees here, but the boiler's still making 120 because there's another loop or another zone that's asking for 120. So we're going to mix some of that. So we're going to take the 120 and 80 and mix it down so we get 100 degrees. And that means that my return water temperature is lower, which means my delta T is higher. Now that's good for a condensing boiler. We're going to have a lower or a higher delta T, which means we're going to have a more efficient system. But there are flow examples of this as well. So let's take a look at that. Look at it from a flow perspective. Fixed speed pump. Now we put a pressure bypass in here because it's an older system with a fixed speed pump. We close a valve. We pass the same amount of water. So we're still sending, we got 10 GPM coming in, and we got 15 GPM here. We got 10 GPM coming in, 5 GPM bypassing, and 10 GPM coming out. So everything's balanced as far as flow goes. But we put a delta P pump in here, and we're going to control the flow based on this valve is closed, but that's going to change the amount of water it's actually dragging. So let's say it's a third closed in both of these examples. So we're only needing 6 gallons a minute to go through here, which means we're only bringing back 6 gallons, or, because the 3 pumps are running, the 3 zones are open, we have 10 across here because 3 is bypassing. So my flow to the boiler is only 6 GPM. So we have a larger delta T, but at a lower flow rate. And the lower flow rate means that the boiler is going to have to not work as hard to supply that load. Again, we could put 3-way valves in here and do the same thing with a 3-way valve. But here's a building that's got a lot of zones. So the biggest zone here, I think, is 50,000 BTUs, and the smallest zone is one of these 2,000 BTUs. So when the building is under full load, dead of winter, everybody's calling for heat, we need 240,000 BTUs. But there are times when we might only need 2,000 BTUs. And if you're watching the webinar we did last week, we talked about delta T's and things like that. So at 240,000 BTUs, the flow rate through this boiler is, whatever it's going to be for that. But we're only using the small zones. We talk about those are micro zones. And that may be a problem for this boiler because, especially with the low mass boilers, it doesn't have enough flow to keep the flow switch made. So as soon as we start taking away zones, we have to look at what's the effect on the boiler as far as delta T's, flow rates, temperature set points, and whether we can actually keep the boiler running. We could solve some of that problem by putting a high mass boiler in or a buffer tank, because we'll have this mass here which will allow us to take the 2,000 BTUs and take it off the buffer or the boiler's mass. So that's one solution. Another solution might be this. So now we have a microzone, and if you look in the back of our application guides for Viessmann 200, 222F, and CU3A, you'll see an application that looks like this. And basically what we're doing is we're using the mass of water that's in the domestic hot water tank. So we store water at 140 degrees for domestic hot water, and we heated it up with the coil inside the tank. And when the tank is hot and this zone calls, we actually take heat out of it through the radiator and back to the return side. So what we have is a system that is heated by the potable water's energy. This allows me to control this zone from a thermostat and not put that minimum temperature load on the boiler. So when we use the mass of the water in the boiler and the temperature, and the tank cools off, the sensor in the tank tells the boiler that, hey, I need to make hot water, and the boiler kicks in and reheats the mass of the tank. So we always have a hot water tank with hot water in it, but we're going to use some of the mass of that energy to do this radiator. We might need to put a three-way valve in here again, because if this is only wants 110 degrees and we're storing water at 140 or 160, then we need to temper that. So there you see it in the full application with the microzone on the primary side. So this becomes a fixed set point, not a weather compensated loop. And these are all most likely weather compensated loops. So if I'm looking at variable speed pumping, we often hear the term variable speed pumping used as it's the way we want to go. It's the more efficient way to do things. But we have to look at it especially from a low mass boiler, its effect on the boiler. The boiler sees a change in flow as a change in load. Now, the most efficient I can make my boiler is to keep it at a very steady modulation rate. So it adapts to the building load in a slow, careful process. It doesn't hunt. And the PID logic inside the burner control and the temperature control that's in the boiler is designed to just do that. It's designed to find the sweet spot for the load. If the load changes, it's going to obviously change the modulation point. But under what we call a steady state condition, the modulation moves very little. But as soon as I change the flow rate here in a low mass boiler, the boiler sees that as a change in low. So we have what we can call the galloping boiler room. The pump speed goes up and down, the burner speed goes up and down slightly behind it. And we have this gallop of modulation, both the pumps going up and down in speed and the burners go up and down. So on the primary side, we generally want to keep a fixed speed loop. On the secondary side, we can do variable speed if we want. And what it allows us to do with a primary-secondary separation is we can actually design the system for a slightly different delta T here than here. So if I want a 30-degree delta T on the primary side because I want colder water coming back to the boiler, and I want 40 or 20-degree delta T over here because I want to have a consistent delta T across the heat emitters, that's the way they're designed to be, we can do that. At some point, as the loads go away, so these modulation valves close or the thermostat shuts this pump off, we don't have any energy being used here. The boiler's going to modulate down to its minimum firing rate. You're going to see the delta T shrink because there's no place for the heat to go, and the boiler will eventually shut off because it has no load. But under normal load conditions, we can keep that delta T here a little bit larger, again, which makes our condensing boiler more efficient. Well, then we go back to this drawing. And we see that we got pumps and we got valves and we got a snow melt system. And in our application guides, we show connections like this. So we have all of the end switches from the thermostat, or from the zone valves, connected to the boiler in parallel, so that if all the zones are closed, we turn off this pump and we actually turn off the boiler. But what if we looked at it from this perspective? If we didn't connect these zone valves to the boiler and let the boiler run on its outdoor reset, let the boiler maintain its constant outdoor air reset temperature, then the boiler is more consistent and we don't have fluctuations in the water system. Remember the beginning slide we talked about when the thermostat shut the boiler off, everything cooled down and then everything had to warm up again. If we don't let the boiler cycle by the valves, we can keep the primary loop very, very stable. Now we could do that with valves, or we could do it with a multi-zone pump controller, same interface. This works if all of the systems are the same temperature. Now, in the Vitadens 200 or the 222F or the C3A boiler, the Vitatronic control has two ways to program it, either heating circuits or zone circuits. And there are there's videos online that talk about how the different setups. So I'm not going to spend a lot of time on that. I made a 3-part video on that a little while ago, so you can see that. But if you connect it as a program it as a zone circuit, it doesn't have a call for heat unless it has a contact close. So you might put a jumper in here. Normally you just program as a heating circuit instead of a zone circuit. But if you don't want the mixing valves, then you only have one of those. So now we have an 80 again, a 60, and a 40-degree loop. When I have these different temperatures, then the idea of connecting the thermostat to the boiler makes a little bit more sense. Because if all of these zones are satisfied, the boiler doesn't need to be at 80 degrees anymore. The boiler can be at 60, right? So when we hook up the thermostat contacts, dry contacts from the multi-zone control to the boiler, when I have multiple temperatures, we get the trade-off that we can run the boiler at lower temperatures. So this makes sense. If you have a multi-zone control with different temperatures, you see we connect them to individual points in the boiler controller, and then they will cycle the boiler based on that set point or change the set point in the boiler. So, as long as this contact's closed, the boiler is going to do 80 because these two are lower. The only other one is, domestic, which becomes a priority. But if all your systems are the same temperature, it doesn't make a lot of sense to use those interactions between the boiler and the zones. So what are the reasons why we do not want to connect zones to the boiler? All the loads are the same temperature. Condensing boiler has a modulating burner that wants to be at the lowest firing rate that can satisfy the load. A condensing boiler is more efficient at the lower firing rates because the flue gas relationship between flue gas temperature and return water temperature is closer. And when the thermostat shuts the boiler off, every time it does that, we increase the number of cycles that's happening in the boiler. So the start and stop cycles are overall in a heating season. Every time we start and stop a burner, we reduce its seasonal efficiency. And this is not conducive to making an efficient system. So the most efficient boiler plant I could build would be one that was perfectly sized. It would start in September and turn off in May and just modulate all winter. But that's not typically going to happen. So, but we reduce the amount of short cycling if we don't connect the thermostat back to the boiler as well. But we have to take some things into consideration. Sometimes a load is better with a thermostat input. So air handlers are a good one. They're not consistent loads. We turn the fan on, we raise the temperature in the space a couple of degrees, then it turns off. And we do that over and over and over again. We don't run the fan 24 hours a day, typically, at least at the delivery system of getting heat into the space. We might run it as an air moving at very low speed. Swimming pools, again, non-consistent load. Snowmat systems, non-consistent load. You got a shop, man, I don't know what the heat on when I'm in the shop. So we're going to turn it on, an hour or 2 hours, whatever, before I get there. And then we're going to have some heat in the space. And systems where multiple controllers with various heat emitters. We talked about that temperature difference. So these are the things we have to think about. But what I want you to look at is how the thermostat is like the ignition switch on your car. When I drive my car, I use the ignition switch to turn the engine on and off. And the same with the thermostat, turns the engine on and off, the burner. They're not throttles. They're not modulating controls. They're not controls that are designed to maintain a speed or a temperature. They're designed to say, I don't need you anymore, or I do need you. So when we look at a car, if we used a car and drove it like my thermostat runs the boiler, and when we got to speed, we turned the car off, the car would lose speed, and we turn the car back on, but we'd have to give it more gas to get it back up to speed. It's the same thing with my boiler. When I turn the thermostat off and I turn it back on again, the boiler starts and it's already lost temperature, so it's behind. So you can see what happens is the modulation rate has to work harder. It has to go to a higher firing output to give me the same design or the same capacity in the system. So again, with a modulating burner, more efficient in a condensing boiler at low fire than high fire, this becomes an issue for us as far as maintaining efficiency. Now, again, if I let the gas pedal control it, right? We saw, I already actually kind of covered this point before. The gas pedal has to go farther, like the thermostat closing the boiler off, the burner has to go farther. But if I let the thermostat out of the picture, so let it control the zones, let it control pumps or zone valves, but it doesn't have to tell the boiler to start and stop. You can see the modulation rate stays very consistent. The PID loop in the controller will always try to do the job at the lowest firing rate it can. It works really hard to do that. So if we don't connect the thermostat or the multi-zone control to the boiler itself, because all the systems are the same temperature, then we have a more efficient boiler plant. And what we have to do is get our customers to understand that when we open the thermostat, the boiler doesn't necessarily have to turn off. And this is 50s technology, right? We added the thermostat so we could control that on an on-off boiler, and it helped at the time, but it didn't make anything more efficient. And now we have condensing boilers, it certainly doesn't make it more efficient. If we leave the thermostat out of it, let the thermostat control zone valves or pumps on the secondary side, my space temperature is more consistent because I don't have that warm-up period. I don't have that period where the boiler has to warm up and heat up before I deliver temperature. Your thermostat already has a deadband in there, right? Your thermostat's already going to open and close, and there's going to be a differential in there. And if it opens and the system still has a little bit more energy in it, and it's going to add a little bit more heat to the room, unless we stop the pump kind of thing. But as it closes, the boiler starts, and we're still going to lose temperature in the space because we haven't heated the water to the right temperature yet. It's lost temperature in the system. So if we have the boiler independent of the zone control, then the boiler stays consistent at its outdoor reset temperature. When the pump starts or the zone valve opens, the water temperature is right already. And what will happen is the boiler sees the load and it'll modulate up a little bit to catch the cooler water coming back to warm it up. But it isn't going to have to, hit the gas. It's not going to have to go full throttle. So again, we need to look at, if we don't connect the thermostat to the boiler, if they're on-off points in the space, the boiler will cycle less often and provide better seasonal efficiency if we don't put those two things together. So the takeaway here is we improve the system efficiency by letting the weather compensation control maintain the correct water temperature in the primary loop or in the boiler loop. And we have, as long as the systems are the same temperature, I want to make sure I impress that if you've got multiple temperature systems, then it may make sense to cycle the boiler just because you're changing the set point. Don't worry about the boiler running wild, because if all the zones are closed, the boiler will catch the set point. It'll eventually shut off. So we have everybody's in setback overnight and the snow melt's not working. It's eventually going to catch the set point and shut off. With our high mass boiler, they're well insulated. There's like 3 inches of insulation around our high mass boiler, and with the low mass boiler, there's not a lot of water in there. So we're not dealing with a huge amount of heat loss there to keep the primary loop or the boiler warm. And it's not going to run wild. So your customer's concerned that his thermostats, the boiler's going to run 24 hours a day and it's going to overheat and it's going to cause all sorts of issues. That's not necessarily the case, okay? The boiler will maintain the primary loop at the outdoor reset temperature, and if you set that up right, you know that what happens is you add heat to the system based on heat loss. The colder it is outside, the faster the building loses heat. So the outdoor reset matches the heat loss to the input. So let the boiler control the system. Let the zones control the building. That's the final takeaway here. That's really what it's all about. Again, we see variations if my loops are different temperatures. In this case, we have one loop with multiple zones. And if you have multiple loops and they're all the same temperature, just different types of pumping or valves or whatever, or multiple areas of the building, then let the boiler do its thing, let the building do its thing. The boiler's good at maintaining water temperature based on outdoor reset as efficiency. The zones are, valves are good at getting water in and out of that room. Let them do their thing, right? They don't have to talk to each other necessarily. And that's kind of what I have. And I'm actually ahead today, Scott. Look at that. We have any questions?
Oh, there we go. Sorry, my little pointer was on the wrong screen here, so it took me a while to
maybe you were napping.
Get it back here. It was in a different time zone there. No, that's good, Mark. You did a nice job, man. You got a little bit of time here for some questions. It's interesting that you pointed this out. I just had a conversation with a local contractor here that we deal with quite a bit, and this is in his own house actually. He put in a fairly sophisticated system. And the topic came up yesterday of where are those zone valve end switches going to go on the boiler control? And of course there are options now with the Vitodens platforms and the Vitocrossal 300 platforms where you can use the thermostat, the end switch contacts, or you can go exactly like you were saying here, let the boiler operate based on a keep up versus a catch up with a thermostat controlling that system. So I said, well, why don't you try it both ways? So he had the end switches and stuff like that. He's going to give it a shot in that way, and then after you are confident that that system is operating, let's take those end switches off and let's try it the other way around and see how your system's going to react. So we're going to have a bit of a live kind of case study here as we move forward on the exact point that some of the stuff you just talked about here, Mark. So thank you.
One of the things that with the end switches and the zone valves is that sometimes they do have a purpose. Because if we have, say, a pump, and the pump is connected to the loop, we may start and stop the pump on our control from warm or the shutdown. But if all of the zones are closed, we saw that even the variable speed pump can only go so slow before it stops pumping water, right? So if we have the zone valves, the end switches connected to the pump relay or the pump contactor, if all of the zones are closed, they can shut off that secondary loop pump, not the boiler pump, but the secondary loop pump.
Right.
There's an application where you might use end switches to control the pump, just so the pump doesn't pump a dead head when we're not dealing with a load anywhere in the pumped area.
You don't have no bypass or whatever, then you need to stop that pump so it doesn't deadhead. There's a good point to use that start-stop of that secondary pump. We do have a couple of questions, Mark, if you want to.
I see them. So the first one is, in a nutshell, if the system requires the same temperature, should we not hook up the thermostat to the primary loop? And my advice personally would be no. Let the boiler do its thing. You're going to have to do some education on your homeowner. And to help with that, I created a short little video. It's a few minutes long, and it's called "Why Your Thermostat is Like Your Ignition Switch." It's really not high technical. I primarily aimed it at the homeowner. They can go to our YouTube channel and watch that, and it gives them a concept of why we're doing what we're doing without turning the boiler off necessarily. So I would say that if all your systems are the same temperature, that would be my advice. Now there's some variations to that in building size and all sorts of things in commercial buildings and all sorts of things like that.
Right.
Next question was, recommendation is to have primary, secondary loops for boiler design, where primary system maintain the water temperature as per hottest zone, hottest active zone, I would say, not hottest zone necessarily, whatever active zone is hot. Water temperature in all zones are controlled per T-stat or outdoor reset. Well, when we do the zoning, if we had multiple zones, you're going to have multiple outdoor reset curves within the boiler. So your outdoor reset curves are going to be present in the boiler. You can do it externally through the third-party controls if you want, but the boiler already has that control built into it. So you could say, let's say as an example, I have two different temperature zones. And one is hotter than the other because the outdoor reset curves are different. One is a cast iron, one is a lower panel, temperature panel, or whatever the scenario is. Then, again, you might want to take the multi-zone control contact and send it back to the boiler in that case, because then when that higher temperature zone is satisfied, the boiler set point then drops. It goes to the next lowest set point, next highest set point. So in that scenario, we want to maintain the lowest possible set point, because the lower the set point, the lower the return water temperature again, right? So if we're sending water at 50 degrees or sending water at 70 degrees, the delta T is hopefully we're designing the same thing. So the colder the return water, the more efficient the boiler. So in your case there, I would say you have a hotter temperature loop. When it's satisfied, you interrupt the command for that, and the boiler goes to the next highest temperature loop because you have more than one temperature. But you'll have in the control has 3 zone circuits and 3 heating circuits. So 3 zone circuits are designed for no mixing valves. Or you use a thermostatic valve if you want to control it, and it's designed to say start and stop the boiler based on those zones. There are also 3 heating circuits, which are the Viessmann historical traditional way. And heating circuit 1 is no mixing valves, and heating circuit 2 and 3 have mixing valves. We provide a control called a Viessmann, which if you want room feedback for those zones, you can do that way. But again, it runs to the outdoor reset. So you could have actually 6 outdoor reset curves within the boiler control, or you can have 3 outdoor reset and 3 fixed if you want, or a combination of those things, because zone circuits can be fixed or outdoor reset. So if you're doing a snow melt, you'd make a zone circuit as a fixed set point, or an air handler as a fixed set point. But the idea of the hottest zone, when it's satisfied, the boiler goes to the next highest set point as long as we tell it we don't need heat anymore. So sorry to continue the last question. When will the boiler shut off if all the zones are satisfied? When it hits the outdoor reset set point. So basically, if the outdoor reset says my heat loss today means I need 50-degree water, when the boiler gets close to 50, it's going to start to modulate back because it doesn't need the heat to do it. And if at minimum firing rate, it just isn't going to keep that 50 degrees, it's going to keep climbing, the boiler shut off. And it'll sit there in the off position for a period of time. Into the burner control, there's a built-in deadband for time off so that it doesn't bang on too quickly. And then there's also the temperature differential, so the system will lose a little bit of temperature. The burner will come back on. But when it comes back on, it'll come back on in low fire. It won't kick itself up into high fire because it will know that its water temperature at the common supply sensor, the boiler's low loss header, is going to be really fairly close to what we want to hit. So it'll come back on and run at low fire. If a zone starts calling again, the boiler sees a load, it'll modulate up and down. But if all the zones are satisfied, so the building's at setback and we don't have any heat going on, once the boiler has caught its calculated set point, it'll turn off. Is there another one here?
Just one more, I think. At what temperature drop in the low loss header from the set point based on your outdoor air temperature does the boiler kick back in? So I think it's kind of an idea of some differential.
Yeah, this is a bit dynamic because the control's pretty intelligent. It not only looks at the temperature loss, it also looks at how fast it got there or how slow it got there. When you look in a control loop, we may have heard the term PID. Proportion is how far away from set point before we go from 0 to 100% of the loop control.
Yep.
I is integration, which is historical error. So the control compares the set point actual repeatedly. And if it sees, oh, I'm starting to lose temperature quicker. And last time I looked, it was 1 degree out. Now I'm 1.5 degree out. And next time I look, I'm 2.5 degrees out. I'm losing heat faster. It will bring the burner on a little bit quicker. But if it sees it's losing it very slowly, it may wait a little bit longer because it doesn't have to play catch up. And so it's a little bit dynamic. There isn't a fixed number. You can say, well, it's 2 degrees or it's 4 degrees or whatever. There's a value you can put in the control to limit how fast it does it as a differential number. But generally, we don't play with that too much because the burner logic's going to figure that out on its own. Oh, is there another one? I saw the line go down. One more.
Oh, so there is no differential.
I wouldn't say there's no differential. The differential is a dynamic value. You could see a differential value in the control logic for the zone of the loop, But as far as the burner cycling goes, it's part of a more elaborate control mechanism where it looks at variation. So, I mean, on a really cold winter day when the set point's high, the control might say, I know I'm going to have to catch this quicker because the heat loss is greater. And on a warm day, it might say, I don't have to catch it as fast because I know the heat loss is lower. So it isn't something I can say it's 2 or 4 degrees or whatever it is. It's moving. It's a moving point. So you can't stand in front of the boiler and say, well, it's lost 2 degrees. Why isn't it back on? Right? It's pretty intelligent.
I'll try to add on to that, and you can kind of correct me if I'm wrong here, Mark, but a lot from my first started working at Viessmann, you'd stand in front of I remember the old WB2A Vitodense 200 boiler, and you would fire that boiler up, and it'd be like watching grass grow, trying to see how that burner would start to modulate. It would sit there in low fire, and you'd be like, come on, come on, come on. But there is an kind of a bit of an intelligence there where it detests the cycling of the burner, so it's trying to kind of extend that as much as possible. So if it can do that via a differential, so basically allow that differential spread out a little bit to stop that cycling of the burner, then it will do, within parameters obviously, it will attempt to do that. That's why the differential moves a bit based on some of that historical information and the last cycle. All those types of things are a component of when that burner is actually going to start to fire back up again.
Yeah, and the idea of fixed, exactly, and the idea of fixed differential really goes back to, I only have one power and one power only. So when the burner started, it was 100,000 BTUs, and when it was off, it was 0. 100,000 BTUs or 0. And we had to put the differential in so we could kind of eliminate short cycling. And your DHW load is still kind of like that, because DHW load is a fixed set point. We always want to make 140 degree water. So we cycle the boiler on a value. In our control differentials, we use in a value called Kelvin. And for all you guys that want to go home and show your wife you actually learned something today, Kelvin is a measurement of temperature. But it's an absolute value. And we use it for differentials where people don't want to reference an actual temperature, but a variation. Because nobody thinks of Kelvin in real temperatures except astronomers, astrophysicists. Because 0 Kelvin is the coldest place in the universe. Nothing can be colder than 0 Kelvin. So nobody says 2 Kelvin and expects that to be an actual temperature, because that's freaking cold. So what we use is a differential. But here's what you know about Kelvin. Here's what's something to know about Kelvin. First of all, you notice I don't say degrees Kelvin, because you say Kelvin in degrees Celsius, degrees Fahrenheit, whatever, because it's an absolute. Mm-hmm. So that's the first thing you can go home and tell your kids, and when they go talk to their science teacher, they'll look smart. The Kelvin is 1 Kelvin is the same physical size as 1 degree Celsius. So if I want to put a differential of 1 degree or 2 degrees, my control will say, what's your differential between on and off? And the coding will say, for domestic hot water, it's plus or minus 2 Kelvin as a default. Well, that's actually plus or minus 2 Celsius in real numbers, but we use Kelvin so that it's not confused with a set point. So 1 Kelvin is the same physical size as 1 degree Celsius. So when you see a differential in our control, there's a number that's based on usually a fixed set point, like a domestic hot water set point. But when we start seeing it with outdoor reset controls, it's dynamic. It moves depending on the outdoor temperature and what the expected heat loss is, how fast it's catching the set point, how fast it's losing the set point. All those things are dynamic.
That makes sense. I think there's one more question here. Oh, maybe more. So if there's a question, I guess following up or from the last one. So if I set the boiler purely on low loss header sensor, or basically you're essentially a primary or a secondary supply sensor picking up that temperature going out to your heating system on a primary secondary system. So if you put that sensor out there, and that was feeding back to the boiler as well as the outdoor air temperature set point, then I can skip connecting that thermostat to the boiler again, to act as an on-off switch.
Again, if all the temperatures in your building are the same, so every part in the building is cast iron radiator, so you really have one heating curve, right? And yes, then that would be the best way to do it. it doesn't matter how much is zoned those cast iron radiators, whether they're individual rad valves or a thermostat on the wall, an electric valve, or a pump that turns on and off to circulate water to the living room. Let it do that. But it doesn't have to tell the boiler it did that, because the boiler will see the common supply sensor. Remember, the common supply sensor in the low-loss header is a mix between the building circulation and the boiler circulation. So it's always a blended temperature. And that's one of the bigger differences between the Viessmann 100 and the Viessmann 200. The Viessmann 100 doesn't have a low-loss header sensor. It uses the boiler sensor. So it's a little bit slower in reaction time. But the common supply sensor on the low-loss header, or even if you're using closest space T's, strap on the downstream side of the loop that goes out to the building, that gives you, the boiler knows what the blended temperature is, and it can be very, very accurate in its modulation. So I would say yes, if your low-loss header sensor in the low-loss header and your boiler is programmed for an outdoor reset for whatever type of heat emitters you're using, then yes, you don't have to connect the zones to the boiler. Let the boiler loop do its thing. Let the zones circulate water to the loop. How often do you see oversized pumps? Oh, yeah. On a boiler side, causing short cycling. The oversized pumps don't necessarily issue with short cycling, but what they do is they reduce the delta T, right? So if I want to have a 20-degree delta T or a 30-degree delta T on the boiler side, and I oversize the pump, and oversizing meaning it's going to pump more volume at the head loss I have, right? Then yeah, I see lower delta T's. That's not really necessarily connected to short cycling, other than it's pushing water to the low-loss header faster. But where we see short cycling is when the delta T is too wide. And then what happens is the boiler catches the set point because we're not moving water fast enough. And that's usually cycling on the boiler sensor. And that was kind of what I was alluding to before with the undersized pipe on the domestic side. If it can't get rid of the heat, it's going to turn itself off, right? Mm-hmm. So oversizing a pump is more of an issue with delta T than it is for short cycling, but I see it a lot.
Yeah, I see it the other way too sometimes. You can see some, if you were kind of looking at a smaller boiler, like residential ones, you see a lot of, the older WB1B boilers, for instance, not necessarily the new ones because they have a built-in pump. But you'll notice some of these smaller boilers, a very popular pump would be the little Grundfos 1558, UPS 1558. But if you do the calculation on that, you're trying to get a maximum flow rate of about 6.2 gallons a minute on some of those boilers. With the head pressure drop at 6.2 gallons a minute, and you compare that to the pump curve of UPS 1558, you're actually not going to reach 6.2 gallons a minute. So if you're putting those combinations of systems out there, that system was never actually overpumped. It was actually underpumped as far as the primary side. But the boiler, we didn't have problems because the boiler would just work off of the delta T at that point. So you kind of see sometimes based on both of those, you might see something where you got something that's got that delta T really down, where other pumps are a little undersized and you're just working off of a wider delta T.
Okay, there's a question here. If the boiler water temperature primary loop is measured to determine when the boiler needs to turn back on, what prevents the temperature in the secondary loop from dropping when the primary loop remains warm with the boiler and boiler pump off? Well, the boiler and the boiler pump will stay on, right, if we're not connecting the zones, and maintain the primary loop unless we don't have any load. If we just don't have any load, or the load is below the minimum firing rate of the boiler, it's going to cycle off. So your primary loop is very consistent. Your secondary loop, yeah, it's going to cool down and warm up based on how many zones or what zones are calling. But you got to know that in most of our buildings, in the wintertime, we always have some kind of a load going somewhere, even if it's just a wild rat at the doorway. So you have circulation in the secondary loop most of the time. It may not be a whole lot of energy that it needs, but you're right. If you've got 4 zones in the house and all 4 zones, the thermostats are closed, the secondary loop's going to cool off. But what happens is when the boiler's primary loop is warm, when that thermostat opens or closes rather, and the zone valve opens or pump starts, then we're going to get water from the low-loss header at the right temperature. We're not going to get water that has to catch up by 5 or 6 or 10 degrees before it can actually get water to the radiators. So if I understand the question correctly, and if I don't, then kind of ask me again, because I think I understand that you want to know what happens to the secondary loop temperature. If the boiler's turned off, yeah, everything cools down, right? And that's the idea of not connecting it to the thermostat. But the primary loop stays at the outdoor reset temperature, which means that when the zone calls, the water temperature is already hot enough to supply water to that radiator. This is great. Lots of questions.
Yeah, we got some more. Just kind of bouncing back up here, trying to get them. What we got here? So what are negative impact when we increase boiler GPM above the design flow rate? So I guess if we're over pumping a boiler, I think that's the question. I'm assuming
again,
it's on the boiler side.
Two things happen. The first thing is you reduce the delta T. So the boiler, you're pushing water through the boiler heat exchanger so quickly it actually can't put heat into it. The second thing that happens is we get velocity issues. Every piece of pipe or every valve or every heat exchanger, if we over pump it, friction is going to mean that we're going to increase the delta, the friction loss. We looked at that at the beginning, but it also means that we're actually could have noise. So we could have what we call velocity noise. So you see a lot of people, and they complain because their system's making noise. Every time the pump runs, the system's making noise. That's almost always the fact that their piping's undersized for the pump they're trying to push through it because their head loss is too high. So we get a lot of friction noise. So yeah, you get lower delta T's and more wear and tear on the inside of the pipe or the heat exchanger and more noise.
Some undesirable things.
Yeah. Nobody likes a noisy boiler, right?
No.
That's why Viessmann spends so much time making them quiet. Anything else?
I think they ran out of questions.
You ran out of questions.
Yeah. There were 3 there, but they were all based on just that last question, just more specific to, boiler side, et cetera, design flow rate information. So they're all, that last question, I think, or your last answer answered those other ones as well.
And some of those are from Dinesh, and he can call me and ask me because he calls me every day anyways. Don't you, Dinesh? Not every day.
Just easier this way. Yeah.
Yeah, it's just easier.
Hello, Dinesh. Yeah.
Well, if there aren't any more new questions, I don't know. Do we supposed to type the answer to all these now? Or
I'll probably have to end up typing those out. I will.
Because we'll have to see how the questions come in because you're going to get all of this video anyways. It's going to be available, but it would be nice to have the written answer in the questions. So
yeah,
okay. We'll
figure
out how to do that because Scott and I are still rookies at this Zoom system. We switched recently from another system, and this is we're all rookies at this one. So we have to rely on our friend in the U.S., Miranda, who's the expert.
Yes, Miranda, our guru. Yeah. So
you guys
expect a call from us.
Yeah. So if you guys don't have any more questions, I don't have any more answers. How's that?
All right. So I think we're going to be doing this again tomorrow.
Not this one.
Mistaken. Not this one. We're going to change up. Yeah, that's right. It's me tomorrow.
We're going to look at the sunshine tomorrow, and I get to answer the questions. And this will be the reverse of today because Scott's way more experienced on solar than I am. I have a guru in Waterloo here that I do rely also. So Steve Royce, who's our solar guy in our commercial department. If I have a solar question, I go to ask him. He's just like 50 feet from me. So
right on. Yeah, that's good to have. So we're going to have tomorrow, bring your SPF if you're joining us, just to make sure. We're going to be talking about some solar, changing it up here a little bit. So we'll look forward to that.
Do it all again. So we're going to have this same one and then the solar one right behind it next week as well. So
back to back.
If you know somebody that wanted to be here and couldn't be here, they have one more opportunity to see both of these. Okay. Thanks, guys. I appreciate you being here.
Yeah, thanks so much. And excellent questions, and we'll catch you next time. Bye-bye.